Finally, in this last section in this chapter, I want to say a little bit more about the Pauli exclusion principle than I said in section 40.3. This section is 40.8, and again, I'm going to address the Pauli exclusion principle. You recall that we said before that all of chemistry is due to the fact that these levels fill up, and the tendency to want to complete these levels is what gives us our whole dynamics of chemistry. The Pauli exclusion principle is based upon two different types of particles that are identical. One type of particle is called a fermion. It's named after Enrico Fermi, and these particles have a spin equal to 1/2, 3/2, 5/2, 7/2, and so forth, times Planck's constant divided by 2π. So the electron, the proton, and the neutron are the three most familiar particles. They all have a spin of h bar divided by 2, half of h bar, which is this first type. But we have discovered particles now that have spin of 3/2 or 5/2 or even 7/2 h bar that are elementary particles. Such particles that have these spins are called fermions. The Pauli exclusion principle said no two identical fermions can occupy the same state at the same time. That's, for example, no two identical particles, no two electrons could be in the same state, no two protons can be in the same state, no two neutrons can be in the same state. So just as the electrons coupled with the Pauli exclusion principle gave us certain levels in the atom, the fact that we have protons and neutrons that are also fermions that also give us a shell structure in the nucleus, because they can only get so close to one another or in the same orbit. So here I've listed these fermions as particles like this, and this includes the electrons, protons, neutrons, but also neutrinos and muons. All of these are fermions. A boson, named for the physicist Bose, B-O-S-E, is an elementary particle that has a spin of 0, 1, 2, 3, and so forth times h bar. And the bosons like to be together. Examples are the photon, the pion, the kaon. The pion and the kaon are spin 0 particles that jump back and forth inside the nucleus between the proton and neutron and hold the nucleus together. So we have these ideas of the boson, but we also have the photon. Photon has a spin of 1. Bosons actually prefer to be in the same state. And as I said, without the exclusion principle, all the electrons would go to the lowest state and they wouldn't fill up shells. Then without a tendency to fill up shells, there'd be no chemical bonding, and then no biology, and then no life. I want to go a little bit further in talking about this. This comes from actually a deeper principle having to do with the exchange of particles and the relationship that particles have if they're identical in quantum mechanics. And if they're exchanged and you've got a minus sign in the probability function, it's called a fermion. And if it's a positive sign, it's called a boson. These are called the statistics that are associated with the particle under their exchange.